Welcome, everyone. I'd like to get started. Welcome to this CREDC Cyber Resilient Energy Delivery Consortium seminar. I'm thrilled to be able to welcome Nancy Levinson here today. Nancy is Professor of Aeronautics and Astronomics at MIT. But Nancy does much more than aeronautics and astronautics. As you'll see when you hear her talk, she's a systems engineer, and in a sense, she thinks about very deeply the topic of safety and how one designs, assesses, and determines whether particular systems are safe. This is a topic, of course, that is of great importance to the power grid. As we know, safety is probably the highest constraint of what we have to achieve. And in CREDC, we have to make sure that our systems are safe, even when there may be malicious attacks that they have to undergo. There's much more I could say about Nancy. She's the author of two very well-known books. She's the author of a methodology that's widely used in industry with regard to creating safe systems. She's applied these techniques in a wide variety of applications, from aerospace, from transportation, to chemical plants, to nuclear power, medical devices, and many more. But I think you'd rather hear from her than me. So welcome, Nancy. We're thrilled to have you here, and we look forward to your presentation.
Thank you. So I'm going to talk about how to engineer a safer and more secure world. You've carefully thought out all of the angles. You've done it 1,000 times. It comes naturally to you. You know what you're doing. It's what you've been trained to do your whole life. Nothing could possibly go wrong, right?
Nothing.
So I really like this because in addition to it itself, the beaver is MIT's mascot, nature's engineer. So.
In our field, it's squirrels and transformers.
All right. So how did I get going in this sort of weird world and weird problem? And it really started 36 years ago. In 1980, I got my PhD. And I was doing, in computer science, I was doing sort of normal, formal methods, software engineering things. And I arrived at my first teaching position, which is the University of California, Irvine. And I had been there about a week. And I got a call from someone at Hughes Aircraft Company, which was in the area. And they said, we're building this torpedo. And it has 15 computers on it, microprocessors. And this is more complex than we've ever built before. And we think we have a problem of software safety, but we don't know how to solve it. And we want your help. And I said, I'm sorry, I don't know anything about this. I do formal methods. And I'm a mathematician, and I don't know anything about torpedoes. And they said, well, we have some money. So I said, well, let me put Professor Levinson on the phone. She's the software safety expert. And so I became an instant software safety expert, and I was ready to do something else because my dissertation had just been plagiarized, and I couldn't publish it, and I was bummed out with the topic anyway. So I thought, well, I'll look at this for a few months. And it wasn't much money. And what turned out is I learned a lot. I don't think I helped them at all, but I learned a lot. And then from really some of the best system safety engineers in the world, which it turned out there was a whole field of this that I didn't know about. And then after about a year, they called me up and they said, well, Nancy, are you interested in what happened with this? And I said, sure. And they said, well, we took it down to the torpedo proving grounds off the coast of California. And every time we fired the torpedo, it came out of the tube, it turned itself off, it went to the bottom, and it just sort of lay there. And I said, it's safe. And they said, yeah, but the Navy doesn't want to pay for this safe torpedo. So So I said, well, what did you do? And they said, well, we do what we normally do. We took off safety devices enough until we got it reliable enough and safe enough. And so this was one of the first times it seemed to me that, first of all, I really understood the difference between reliability and safety. And not only were they different, but they could conflict. And the other thing is, well, I didn't have anything better to do since my dissertation was plagiarized and I didn't know what I wanted to do anyway. I'd spend 6 months on this problem because it seemed like waiting until the thing was finished and then doing something about it really wasn't going to be a very appropriate, good solution to the problem. So I thought, well, I'll spend a few months on it. So that was 36 years ago. And I think I finally solved it. So now I'm ready to retire because I've gotten my solution finally. And so that's what I'm going to talk to you about and tell you about is the solution that I came up with. And I'm going to start with the conclusions. So this is what I'm going to say in the talk, and then I'm going to go back and fill in the details. And the first conclusion is that complexity is reaching a new level, as we all know, in these systems. Old approaches that we're using are less effective, and there are new causes of accidents appearing, especially related to the use of software. So because of that, I believe we need a paradigm change. Excuse me. We need to change our focus from increased component reliability to enforced safe behavior, which is really a dynamic control problem, and I'll explain what I mean by that. But what do we get from this? Well, by doing this, we can create a whole bunch of new analysis and engineering approaches that's much more powerful, inclusive, orders of magnitude less expensive, which surprised me because I thought since they were more powerful, they'd be more expensive, and they aren't. They work on very complex systems. I'll show you some of the examples. And we can design safety in from the very beginning, which is what we need to do. Then it turned out a couple years ago, a graduate student of mine, Colonel Bill Young of the US Air Force, said, you know, Nancy, this will work for cybersecurity. And I said, I don't think so. And they say, oh, yeah, it will. I said, all right, well, show me. And he did, and he's right. So I'm going to talk about how we apply the same approach to cybersecurity. And it's a paradigm change in for both of these fields, especially security. And then, of course, the final question, the most important is, does it work? I mean, it's nice to have new approaches, and you publish all kinds of papers, but does this really work on real systems? And all the evaluations and experience so far shows that it works much better than what we're doing today. So that's the conclusions. Now let's go fill in some of the details. And the first thing is we need to understand what the problem is. You cannot solve a problem unless you understand what the problem is that you're solving. So, first problem is that all the current tools that we use are all 40 to 65 years old, but our technology is very different today. So FMEA is late 40s, right after the war. Fault tree analysis, HAZOP, you may not know what these are, don't worry about it. Event tree analysis, bowtie, which is just the combination of these. All of these assume that accidents are caused by component failures. And they were all created before 1970. There's nothing new. Nothing new has come since then. Except that the world changed since then. And starting around 1980, all of a sudden, the world of engineering changed. We introduced computer control to a great degree, exponential increases in complexity of the systems we were building, lots of new technology, and the human roles in systems were changing. Humans weren't just following a bunch of procedures. They were monitoring and supervising complex control systems, usually based on a computer. Now, let's start with what do people do now? Or what did they do then? What is the basis? And underneath all of this is this model of causality of accidents, which actually comes from the 1930s, the Domino Model. And it basically says Accidents are caused by a bunch of events like dominoes, each one leading to the next one. So this was a DC-10 accident loss over Paris, France. The cargo door wasn't closed properly, which caused the floor to collapse, the cargo compartments under the passenger compartment. But all the hydraulics were designed to go through the floor. So the floor collapsed, which meant that the hydraulics failed, and nothing the pilots could do at that point, and the plane crashed. All right? It's a event-based model of failures, events. And so here's another example. This is a little more, a different example of a tank rupture. And here's the first event: moisture gets into the tank, which causes corrosion, which causes weakened metal. That, you can have ands and ors in this thing. That plus a certain operating pressure leads to the tank to rupture, which then leads to fragments being projected, which leads to equipment being damaged and personnel being injured. It looks perfectly reasonable, right? So if this is the problem, how do you solve it? What would you do? People in the room. Anyone? What? I'm saying.
Seasonal maintenance, so that moisture never really creeps in, and so on and so forth. The chain of events that happen from that moisture doesn't really happen.
All right. Well, the simple way of saying this is you prevent the events. You prevent the failures. So you either get rid of these events, or you put barriers. If it's a chain, if you put a barrier between two events, then that failure can't cause the next failure. Simple. Pretty obvious. And so what do we do with it? Well, one of the things we do is then, I just annotated this with things we might do, and these are all standard classic safety engineering techniques. Moisture, use desiccant to keep moisture out. Corrosion, use a non-corrosive material, stainless steel or something. If it's weakened metal, you over-design. Classic engineering method, over-design so that it won't fail. Operating pressure, reduce the pressure as the tank ages. Tank rupture, use a burst diaphragm that bursts before the thing actually explodes and minimizes damage. Fragments projected, provide some screen around the thing to keep the fragments from being projected. Equipment damage, locate the equipment away from the thing. Keep personnel from the vicinity of the tank. And this looks perfectly reasonable to everyone for this kind of electromechanical physical system that we had. And it works. There's nothing wrong with it. It doesn't work perfectly because as time goes on, well, we said we're going to reduce the pressure, but we're under a lot of competitive pressure right now, and we've got to get the productivity up. And yeah, we said locate the tank away from other equipment, but as time went by, that wasn't very convenient, so you started moving other equipment in. Personnel started coming into the area, but it still seemed pretty good. And it works because, but what if there were a computer here? And instead, it works because we know why these things happen and how to prevent them. What if there was instead a software here that instead of a burst diaphragm, it measured the pressure and relieved it itself? Now, software didn't fail, right? So why? How do I prevent that? How do I stop that from happening? Well, now the problem's a little bit different. So the traditional approach to safety, you view safety as a failure problem. We get this chain of directly related events. We establish barriers between the events, try to prevent vulnerable failures. The problem is that the limitations are the systems are becoming more complex Accidents often result from interactions among components, and it's not failures. And it's too complex to anticipate all the potential interactions. I'll show you some examples of this in the next few slides. And it omits or oversimplifies important factors. Human error isn't there. Human error is not just a random failure. New technology, culture, and management, which we know have big impacts on accident. Evolution, adaptation over time, changes over time. So accidents are not just the result of random failure. It's only a random failure, so it'll never happen again. So here's some examples. This is the Mars Polar Lander. Suspiciously, the Schiaparelli accident, recent one in the last couple of weeks, looks just like this. I can't believe they made the same mistake. There's got to be something down deep that's different. You have to slow down the spacecraft in order to land safely. So it's coming in very fast, speed of a bullet, all right? So there is some Martian atmosphere that slows it up a little. They have a parachute that slows it up, that's released to slow it up. There are descent engines, which are controlled by the software. The descent engines work against the direction the lander is going, the spacecraft is going. So it's like reverse thrusters on a plane that slow it up. Now, the software has to know it's landed. Because what if this thing lands and the descent engines are still on? What's going to happen? It's going to shoot up and fall down again and crash. So there's these very sensitive sensors called Hall effect sensors right on the legs of the spacecraft. And the software engineers were told to cut off the engines when it gets input from these sensors, which was fine, except that there's this false signals, this noise that with the parachute is deployed, there's sort of a jerk on the spacecraft. And so those sensors put out some signals. The software, now why, and the software didn't know what they were, thought they were a real thing, turned off the descent engines when they were still 40 meters above the surface, and it crashed down and was destroyed. Now, why they did that, I'm not quite sure. They didn't tell the software people about that. The engineers knew about that this would happen. But the software wasn't supposed to be operating at that time. I think that may be why. But the software engineers decided to start early to even out the load on the processor. So we lost the spacecraft. Here's another one I really like. So Navy aircraft were ferrying missiles from one location to another. And one of the pilots was told to execute a planned test by aiming at the aircraft in front of him and firing a dummy missile. Now, nobody knew. This software was smart software. And it was programmed and designed to identify that maybe there wasn't a good path from that to the target. So it would substitute a different missile on the wing. So there was an antenna underneath the aircraft. It was right in the way between the dummy missile, which wasn't going to be fired anyway, and the target. So it substituted to a live missile and shot at his friend in front, who luckily was an excellent pilot and he evaded it. Although, you know, as soon as they got on the ground, someone said, how did he get away from that? We got to fix that. But if you look at that, what failed? Every component worked exactly the way it was supposed to work. That's what we're seeing now. It used to be that our systems were simple enough, our electromechanical systems, we could get all the design errors out beforehand. And they were electromechanical, we could test them all. Now with software, you know you can't exhaustively test software. And you cannot think through all the things. These things are so complex and so interconnected and coupled, you can't think through all the possible interconnections. And we've got a new problem here. The Boeing lithium 787 lithium-ion batteries. You may have heard about that. It happened twice. In the first, it was supposed to, theoretically, wasn't supposed to happen for 10 million flight hours, I think it was, and it happened twice in the first 52,000. And this is just one of the problems here. But there are other problems. A module monitors for smoke in the battery bay. Smoke in an airplane is really bad, especially if it gets into the cockpit, because the pilots then can't see and sort of pass out. So they have a module monitoring for smoke in the battery bay, which controls fans and ducts that exhaust the smoke overboard. Okay, sounds good. There's another unit, a power unit, that monitors for low battery voltage. And it finds it, it shuts down various electronics, including the ventilation. So smoke couldn't be redirected out the cabin, and they had an emergency. Luckily, they were on the ground at the time. All right. All the software requirements were satisfied. The requirements were unsafe. I've been doing this for 36 years. I've read hundreds of accident reports, and many of them had software in them. And every someone that software was related, it was a requirements problem. It was not a coding problem. So that's the first really important thing, is everybody's working on coding and testing, and they're not working on the requirements, which is the problem. So there's two kinds of accidents: component failure accidents, we still have them, but we have these component interaction accidents. And they're related to complexity and coupling in our system design. And none of the components may have failed at the time. So we're confusing safety and reliability. In this green circle, there's scenarios that lead to accidents. There's scenarios involving failures, not necessarily unsafe ones. In the pink circle are all the unsafe scenarios. There is an overlap. We have lots of tools to work on them, but it's this over here, B, where nothing failed, that none of our tools work. And everybody's still using all those tools, and they're missing all those accidents. The other thing I just want to say quickly is, do operators cause all accidents? You've all been told. Operators cause most accidents. Pilots cause 80 to 90% of accidents, supposedly. And it's always human error. Is it really? Well, the traditional view says operator is the cause, so what we do is do something about the operator. Fire them if they aren't already dead, retrain them, suspend them, or do something about operators in general. If it's the operator's fault, get rid of them. So we marginalize them by putting in more automation, so they're farther away from the system they're controlling, or we rigidify their work by creating more rules and procedures that they can't follow. Fumbling for his recline button, Ted unwittingly instigates the disaster. The systems view, the new systems view of operator error, is that it's a symptom, never a cause. All behavior is affected by the context in which it occurs. And what we're doing is the role of operators is changing, as is the errors they're making, and we're designing systems. Many of the people in this room are designing, or on the web, are designing systems in which operator errors are inevitable, and then they blame the operators. That's not going to help, because we just, even if they don't survive, we're going to just get new operators who make those same errors eventually. So, bottom line, human error is a symptom of a system that needs to be redesigned. The problem is that human factors people work from the screen out. They look at ergonomics of the piece, they look at the design of the screen, and they worry about how many colors are on it, and they worry about the training of the people. The engineers are looking at screen in, and they're designing this stuff. And what we're ending up with is nobody looking at the integrated system as a whole. And so we're designing this stuff as engineers where we're causing mode confusion, situation awareness problems, inconsistency. We are causing the pilots to make mistakes, and then we're blaming it all on the pilot instead of fixing the real problem. So we need something new. New levels of complexity, software, human factors just don't fit into this reliability-oriented world. And so two approaches are being taken. The one on the left is just pretend there's no problem. Do everything, use all the same old techniques, use the same things, make all the components more reliable, and then just keep going, ignoring the fact we're having all these new accidents. The second approach is at least they admit it, but then try and shoehorn the new technology and new levels of complexity into the old methods. So, and I did that too for a while. I mean, my first thing is, all right, we already have fault tree analysis. We already have all these analysis techniques. Just add software to them. Except it doesn't work because this problem is totally different that we're trying to solve. So let's first look at the traditional approach to coping with complexity. It's called analytic reduction. This goes back to Descartes. It's totally what you've been taught your whole life in engineering and in your science courses. And basically what you do is, if we have a complex system, what do? Well, divide it into pieces, all right? And look at each piece separately. So we divide them either into physical pieces or into functional pieces. And if it's behavior, we separate them into events over time. Look familiar? That sort of looks like my chain of events, and in fact it is. And then we analyze the pieces separately and combine the results. But that makes some certain assumptions there. It assumes that when you separate them, you don't distort the phenomenon. Each component or subsystem operates independently, that their behavior is the same when they're looked at individually as when playing their part in the whole. They're not subject to feedback loops, nonlinear actions, other kinds of things. And the interactions can be examined pairwise. Otherwise, we couldn't put them back together again. All right. Great assumption. Works on all kinds of systems. I mean, it's made modern science and engineering. So I'm not going to complain that this doesn't work. It does, except it's not working on the new systems we're building. The systems we're building are tightly coupled, software intensive, highly automated, and connected. Now, I can tell you, just don't build these. And you're going to look at me and say, oh, yeah, academic. You know, of course you're going to build these systems. So we're going to have to do something besides just say, don't build them. And to do that, I believe we need a new theoretical basis because our systems don't fit the underlying theoretical model that's being used here. It's still hungry, and I've been stuffing worms into it all day. You know, people mean well. They're really trying hard to solve the problems. It's just that they're solving the problems for a different problem. They're solving things that don't, and providing techniques for systems that aren't true anymore, aren't there anymore. So we need new tools for the new problems. So what's my solution? The solution is that systems theory can provide a different foundation. Now, what's systems theory? And first I have to explain that to you because unfortunately most of you have never been taught systems theory, although it is not new. I did not invent it. It actually is about 50, 60 years old. Von Bertalanffy came up with this in biology. At the same time, Norbert Wiener, who's a mathematician, came up with it in math. He called it cybernetics. You've probably heard that name. But that name didn't win out. In the end, Bertalanffy came up with what he called a general theory of systems, and that's the name we use now, but it's the same thing. And what does this say? Well, it's really actually a pretty simple concept. We have some components, and they interact in direct and indirect ways. And certain properties, this is a basic fundamental concept in systems theory of emergent properties. These are properties that emerge when the components interact. They're not in the individual components. You've probably all heard the term in system engineering, the saying, the whole is greater than the sum of its parts. That's what we're talking about. Other properties, you can sum them, and you get a summation. You take each individual, look at it, essentially sum them, put them together, and you get this. That won't work for emergent properties. Safety and security are emergent properties. If I hold up a valve and I say, I'm going to use this valve in my car, will my car be safe? You're going to look like you can't answer that question. I mean, how are you using it? What's it interacting with? What else is there? We have to look at the design of the whole before we can determine whether this thing is going to be safe. So what do if you have an emergent property? You need to control it. And we introduce a controller of some kind that enforces safety or security constraints, either both individual component behavior, because we still have to deal with individual component behavior, but also component interactions. And we have some control actions that the controller can issue to the process and gets feedback about the state of the process. Now, for most of you are engineers, you've had a basic controls class, and you're going to say, well, yeah, that's just feedback control loops. Yep. Underlies control theory, too. So here's an example. If every airline decides that their planes are going to take the direct route to where they're going, and at the time they want, they're going to optimize each airline's schedules. What we end up with is everybody ending up at JFK, O'Hare, and probably in LAX at 5 p.m. And of course, that's not going to work. So what we do is we put a controller that controls the interactions, the tracks that the planes go on, how they go, when they go. And what we do is keep them apart, which maintains safety, and we optimize throughput, which is another emergent property. So every airline doesn't get optimal, but the whole is optimized. And so they're probably going to end up with a better result than if we just had chaos result, or everybody fend for themselves. So they enforce safety constraints, not violating minimum separation, maintain sufficient lift. The level of liquid and ice on tower must remain below a specified level. Toxic chemicals, radiation must not be released from the plant. Pressure in a deep water well must always be controlled. Weapons must never be detonated inadvertently. These are the high-level functional safety requirements. And what we need to do is build a system that enforces those requirements. So what we've done is taken what was a failure problem and made it into a control problem. And that's the basic idea. So here's an adaptive cruise control in a car. Here's just show you this. What I mean is classic control loop kind of thing. If an operator gives input to instruments, gets visual feedback back, we have an adaptive cruise control module. We have some radars giving inputs, providing inputs. The adaptive cruise control is bringing braking signals to the brake control module, getting some feedback back. Brake control module is giving braking signals to the brake. Friction stops the vehicle or slows it down. Wheel speed is a feedback. Adaptive cruise control module is also controlling the power and the throttle and the speed of the vehicle, plus probably all kinds of things. There may be dozens of all interacting control loops. That's the problem. They have this problem in auto, which one of my brilliant graduate students has figured out how to solve in a really easy manner, called feature interaction, where all these features on the car were all designed separately, somehow interact in unexpected and bad ways. So, I mean, who would have thought that on a GM Cobalt, that if you had too many keys on your keychain, it would cause the front passenger airbag not to work? And we've killed several people that way, or GM has. And the complexity of these things is astounding. There are now, on the car you drive, probably, if you drive a new car, about 100 million lines of software. 100 million lines of software. The F-35, the Joint Strike Fighter, the newest, latest military jet, only has probably 20 to 25 million, a fourth of that. Our cars are getting stupendously complex, and they're all using our techniques because the old ones aren't working. So we can also put in, I know you can't see, and I want to spend a lot of time on it, put in Congress, regulatory agencies. Controls are also social controls or managerial controls. And so we can include management, regulation, and other things into our analysis and our models. So again, what we're doing is recasting safety as a control problem. We design an effective control structure that eliminates or reduces these adverse events. And that can involve physical design, operations, management, social interactions. And I just want to make one point. There's a very broad view of control being done here. You can control failures and unsafe interactions through design, redundancy, interlocks, fail-safe design, or which we do now, or through process, manufacturing processes, maintenance, operations, or through social controls. Government or regulatory controls, culture, insurance, law, individual self-interest is probably the best way to get people to change their behavior. There's one other aspect of this thing. In any control loop, there's actually a theorem in linear control theory. Every controller must contain a model of the thing it's controlling. So I call that a process model. It's a model of the controlled process. In a human, we usually call that a mental model. In software, we have it, but you don't ever talk about it. It's usually just a few variables, but it's had to be there. So what happened with and I contend that accidents often occur when the process model is incorrect. So for the Mars Polar Lander, the spacecraft was 40 meters above the surface. But the controller, the software, thought it had landed. So it issued a control action to set off the descent engines. All right? Now, that's a much better model of why software misbehaves than the software failed. I don't know what that means. I mean, software is an abstraction. How do abstractions fail? All right, there's 4 types of unsafe control. The control commands required for safety aren't given. The unsafe ones are given. Potentially safe commands are given too early, too late, or control stops too soon. And I don't have time to go over those because I want to give some examples. But what we do is take that and we look at, this is just a more detailed control loop. Here's a controller, actuator, sensors, the controlled process. There may be other controllers interacting with this. And what all I did was annotate each of these of what could go wrong. The process model could be inconsistent, wrong, incorrect. The algorithm could be inadequate. These are the control actions, could be inappropriate, effective, missing. Actuator may not work, delayed operation here, conflicting control actions. Component failures, we still have component failures. I haven't gotten rid of anything, I'm just adding. Changes over time on the feedback, measurement inadequacies, feedback delays, missing feedback, and so on. And what we do for the analysis is we just build that control structure like you saw for the braking system, the adaptive cruise control, and do an analysis on that control system, that control loop. And that's all we're doing. I'll tell you, as I said, a quick example. The whole underlying model, replacing the chain of events model, is called STAMP, System Theory Accident Model. It's just a new, more powerful model. It's based on systems theory rather than reliability theory. It treats accidents as losses, or losses as a dynamic control problem versus a failure problem, and it includes all these things: this socio-technical system, common interaction accidents, software system design, human errors, and so on. And what we can do is take STAMP, which is just a theoretical model. We can build a bunch of tools on top of that, like new accident analysis tools, new hazard analysis tools, new security analysis tools, new identify leading indicators of increasing risk, organizational cultural risk analysis, put those together into various kinds of system engineering, risk management, regulation, and so on processes. And one of the good things about this is we can start it early. So this is just pretty standard. 70 to 80% of safety-related decisions are made in concept development. But we don't normally, here's concept requirements, design, build, operate. We normally don't start doing it until at least we have the requirements, and usually we need a design to use the current techniques. It's too late. The cost of making changes late is enormous. Rework is the biggest cost factor in any system engineering project, and it's why things fail, or go over budget at least. And so what we want to do is build safety and security in. I mean, the same thing with security. We tend to spend a lot of time in security on attack response. Maybe we add some bolt-on stuff during the build, at the end of building the stuff, bolt on some security techniques. Almost nothing is ever done in designing this thing to be safe and secure from the very beginning. And that's what we can do with this new approach. Now, I'm going to go over one example quickly to show you what the results are that you get. This was a non-advocate safety assessment of the U.S. ballistic missile defense system, the new missile intercept system that we have. It was done just prior to deployment. The hazard was inadvertent launch, and nobody knew how to do this. This is an enormously complex system, probably one of the most complex we've ever tried to build. And they had to do the safety assessment for inadvertent launch, but nobody knew how to do it. So I came up with this idea around the year 2000, but I didn't say anything to anyone because it was so bizarre and weird compared to what people have always done that I thought, well, they're going to say, oh, yeah, Levison, she did good work when she was young, like inversion programming things, experiments. But now that she's getting older, she's sort of lost it. And so I didn't tell anyone because I wanted to try it on some real systems. I wasn't really planning to start with something quite this real and this complex. So someone did this without telling me that they'd done it until afterwards, because I would have murdered them. The analysis was done by just 2 people. What?
It's being recorded. Be careful.
That's right. That's right. I'm really actually a very pacifist. I would have only written them a nasty note. The analysis was done by 2 people over 5 months. They found in this 2 people who didn't know anything about the system to begin with, found so many problems with it that deployment had to be delayed for 6 months. It cost them $200 million just to fix the stuff which was really low-hanging fruit that they found first, and then they hired them to do this for the rest of the system. But what they found was exactly what we said. There were lots of scenarios where all the components were operating exactly as intended. It also found the component failure scenarios that the old techniques find, but those didn't find the other ones. So here's, very quickly, the control structure, and I don't have time to go over it in detail, but there's a command authority up here. These are our commanders. They provide policy and other things to the operators. The operators send commands to the fire control computer, which gets stuff from the early warning system and the radars to try and detect that a missile is coming into the US. The fire control computer, if it thinks it has a missile coming in or several missiles, it's called track. They have an active track. They send a command, and the one we're going to be concerned with is fire enable here, to the launch station, which controls the flight computer, which launches an interceptor, and there's also a launcher here, and some simulator that's always going on to make sure this thing is still working. So the hazard of inadvertent launch says that the launch station issues a launch command to the flight computer when there isn't an active track, right, when it isn't a threat. And that can occur if the fire control computer issues a fire enable command. Now, so we take those 4 types of unsafe control actions, and let's look at fire enable. If it provides it, it's not unsafe. So it doesn't provide a fire enable. There's no unsafety with respect to inadvertent launch. It didn't tell anyone to launch. If providing it when there's no threat detected, wrong timing, discover the track is spurious, they send a fire disable one. So they send a fire enable. They decide, oh, this is spurious. This is a friendly thing, a flock of birds or something. So we're going to send a fire disable, but they arrive in the wrong order. And the other one isn't applicable. So let me just give you an example of what we come up with, what the results are. Here's a fire enable causing the hazard. The process model incorrectly thinks the threat exists. So the fire control computer is intended to send the fire enable command to the launch station when it receives a weapons-free command from the operator, the human operator. FEMA just said fictional missile intercept system. The Defense Department gets a little unreasonable about my showing the real system. So this is a fictional system, but very similar to the real one. The specification requires that there be an active track, but the software supports declaring tracks inactive after a certain time with no radar input, right? It's disappeared, the thing. After the total predicted impact time for the track, it's too late. Or after a confirmed intercept of the thing. Now, it turns out the operator, they didn't consider one case, which is if the operator deselects all of these options, in that case, they will send a fire enable. It's just a missing case in the software, an odd case in the software. It wasn't disallowed. It probably should have been, but no one thought of it. And it could cause a catastrophe. So what we want to do is fix that. I have some other examples, but not enough time to go through them. Now, just to show you what other people do and the standard techniques do, this is from the standard that's used to certify aircraft in the US. And it's for the brake system control unit. This is an example right from the standard. It provides requirements like the probability of a brake system control unit fault causes loss of braking shall be less than 3.3 times 10 to the minus 5 per flight. And you saw all of these are just probabilistic requirements They don't know what to do with software. So they say, well, we'll just develop software to a certain rigor. And that's development, which mostly means you do a little extra testing on it. But does nothing about requirements, which are the problem. The same thing using STPA, our technique. Brake command, this is just one example, not provided during landing roll, resulting in insufficient deceleration and potential overshoot from you don't brake, in other words, when you land, after you land. Scenario 1, there's an auto brake, believes the desired deceleration rate has already been achieved or exceeded, and so on. The reasons may include, and it gives some reasons why this could happen. And what we do then is generate requirements for the software and for the system. But behavioral requirements, not these useless probabilistic requirements. I don't know what to do with that kind of probabilistic requirement. Sorry, I haven't got time to answer your question yet right now, but I will later. So I'm almost done. So as I told you, Bill Young decided this could be used for security too. Safety is concerned with unintended actions by benevolent actors. Security prevents losses due to intentional actions by malevolent actors. The only key difference is intent, but our common goal is to get rid of the losses. The goal is not to keep people out of our system, which is what we concentrate on now. I don't care if they get in my system. What I care about is maintaining that the critical functions of the system are able to be maintained. So what we do is the same kind of analysis on here, but let's say each of these, a feedback delay, that could be unintentional, but it could be on purpose. We add more scenarios, but we do the exact same thing as for safety. So stucknet, I'm sure most of you know what that is. The loss was damage to the reactor, in this case it's the centrifuges. The vulnerability was that centrifuges are damaged by spinning too fast, and they put a virus in or whatever it was to make them spin too fast. Constraint is centrifuges must never spin above the maximum speed. The hazardous control action is issuing an increased speed command when it's already spinning at the maximum speed. One potential causal scenario, incorrect process model. It thinks it's spinning at less than the maximum speed, and so it issues an increased speed command, which is what apparently this did. It could be inadvertent. It could be deliberate. I don't care whether it was on purpose or not. I don't want this thing damaged. I don't want my nuclear power plant to melt down, whether it's deliberate or not. I want my brakes on my car to always work, whether there's a hacker on it or whether it isn't being hacked. There's potential controls we could put in here. Mechanical limiter, an interlock, an analog RPM gauge, which would independently measure the speed of this thing and provide feedback. Doesn't work. STPA is being used on a large variety of industries, just about everything now. Most of the auto companies are all now using it. Is it effective? Well, there have been lots of comparisons made, and every one STPA found the same causes as the old traditional hazard analysis methods, plus it found more. The most interesting one, I think, for this group is something done by EPRI, the Electric Power Research Institute, because it's Power Institute, and they compared it. They took a nuclear power design, and they gave it to experts in each of these techniques and asked them to do a hazard analysis on it. STPA did much better, but what's most interesting is it turned out, they told them afterwards, there had been an accident in this plant, which was very serious, and only STPA found that scenario. And why? It was the only one that could, because it was a design error. It wasn't a component failure problem. Same thing have happened with lots of evaluations for the security parts by US Cyber Command. So there's a book I'm not trying to sell books. I made a deal with the publisher, especially because I'm an academic and I care about students. And you can get a free PDF download. All you have to do is Google Engineering a Safer World, and it comes up #1. Not surprising, for the free one. Amazon.com is later on, down farther. But that's fine. You're welcome to do it. We have a workshop every March, and it will be at the end of March this year at MIT. It's free. There'll be tutorials, presentations. There's usually about 200-300 people attending from all over the world who are using this stuff. And there's a URL, and I'm done. I didn't leave any time for questions, unfortunately.
Perfect presentation, thank you. I knew we could, and there's lots of questions. So let's see, you can ask questions. I think you're supposed to speak into your microphone. And Nancy, do you have to push something, or you just speak into your microphone? So push a button. Okay, we'll start with Cheyenne since I saw him first, and then people raise their hands, and Nancy, you can manage your questions. Is that okay? And then we may have questions.
Fine.
You see questions are coming online as well. You see you have a big audience.
Okay, I have to see those.
Well, I can read those. We'll alternate.
I have to get my glasses out.
Okay, Cheyenne, please go ahead.
Thank you for the very nice talk. Casting this reliability problem as a control problem sounds like an interesting idea and possibly very useful as you're demonstrating in your talk. Presumably, the control problem that comes up once you formulate it as such is very complicated, right? It will have nonlinearities, switches, etc.
Absolutely not. What you saw was an astoundingly complex system, and that's the scenario. One of them was generated. I have some more I can show you, just as simple. It is not a mathematical control problem, because this is design errors. You're not going to get a mathematical equation for design error. What we want is, we use the control theory and the control ideas to help people generate scenarios in their mind. Essentially brainstorm, but help them brainstorm in a step-by-step fashion to identify scenarios. Can we guarantee that we found them all? Absolutely not. Would I be willing to bet a fair amount of money that we will find more than the techniques? That's what the techniques now do. That we use now, that we find more, I will bet you a large amount of money, because every time it's turned out it finds more. And unfortunately, I mean, there's no mathematical solution to this problem. If there were, it would be, we probably would have found it a long time ago. It's an engineering problem, and engineers get together when they design these systems, and they say, well, what should we do? Should we use this or this? And you do the analysis, and you say, well, looks like it's better to do it this way, but then you do some more design. You may have to back up, because now you decide, no, maybe the other solution was better. I mean, that's what real system engineering is like in the field.
So let me, to be fair to the remote audience, because I think it's quite big.
No notion of likelihood. Oh, yes.
If there's no notion of a likelihood of an event, how can we ever establish that a system is safe enough or secure enough?
You know, people want a number to make a decision. And so you saw, they make up those silly numbers, 3.3 times 10 to the minus 5, that the thing will break when they requested. How do you know that you've achieved that number? Absolutely don't know. And most of these numbers are made up out of whole cloth, because people want a number. I have been doing this for 36 years. As I said, I've been on big accident investigations, Deepwater Horizon, Columbia. I mean, I've done, and lots of hundreds of small accident reports. Every single one had a probabilistic risk assessment that said this accident could not happen in exactly the way it happened. And the worst part is that in many cases, there would have been a simple fix, but because they convinced themselves it couldn't happen, they never put in the design fix or the protection. And that's really sad. So you're right, you can't. And I wish, there are certain things that are unknowable. When we had electromechanical systems, we had historic data, we knew how they would fail, the components fail, we could add the things together, and you could get a number. And that's what's killing people now, because they can't get a number anymore. I'm sorry, I don't know what to tell you. Don't use software.
Sherry,
Build simple systems. That's the only solution.
go a little to 5 after. Will that be allowed? Okay, then Grace, please go next, and then Sibin, and then Hui. So Grace.
Hi, this is a very interesting talk. Actually, I was going to say, how can you put in the design to predict the outliers or things even unexpected from happening in the future?
This is a worst case analysis. We start from the worst case and we work backwards. So we have the outliers. We start with the outliers. It's not a forward analysis like a FMEA, failure modes and effects analysis, where you look at all the things that could happen, all the failures and stuff. First of all, I can't do that in systems today. Amazingly expensive. And you just can't do it. It's not practical. But this is backwards analysis. Take the worst case. The missile is launched inadvertently. How could that happen? And we can find the scenarios in the logic that would lead to that inadvertent action. Now we have to make engineering decisions. First of all, we have to figure out how we're going to design it out. Hopefully, if we do it early enough, it's easy. The problem with the missile defense system, it was ready to be deployed. That's why it cost so much money to fix it. If you haven't designed the thing yet, you just design it right to begin with. It costs $0 to fix it. But even if you've waited, you can still do this, but you're going to have to make some engineering decisions. And this, do I do this? Do I do this? Do I worry about it? I don't have an answer for that. I know that on an aircraft get struck by lightning. So we put lightning rods and we put lightning protection on an aircraft. In the whole history of aircraft, they've never been hit by a meteorite. Could they be? Yeah, theoretically. But I'm probably not going to put a lot of money into that solution. So I look at the severity, and I look at, it's not really likelihood in terms of likelihood, some number, because we don't know that. But there is some kind of historic information usually. The problem with software, of course, is we have historic failure data for components, hardware components. Software is always new. That's why we wrote it. And the problem is, if we do reuse it, it's probably not going to be safe. Anyway, the Ariane 4 software was perfectly safe in the Ariane 4. When it was used on the Ariane 5, it kind of led to the destruction of the spacecraft on the first flight, because the spacecraft design was different. So reuse of software is not safe, as it is for hardware. I mean, we have just, many of you are computer people, and we've just created a mess for the world. And for engineers, there are really a lot of problems, but we've also created really a lot of opportunities. So
We have another one. Sibin?
Hi. So when you and your collaborators applied these to, like you said, the security domain, do you think this methodology works better for certain classes of security problems very well and not others?
absolutely, absolutely. I think, now I'm not sure Bill would agree with me, but this is my opinion. I know this works for what the Army is calling. They say, yeah, but what about information security? And I'm doing helicopters for them. I said, do you really care whether someone has stolen the social security number of the pilot? I mean, this is not an information problem. It's a problem of somebody, some enemy, doing something to your helicopter or the weapons, network-enabled warfare, to make the weapons go toward friendly troops or something. Those are these kinds of problems. Information security, I don't know. But I know there was one test by the DoD, Cybercom. It was a real satellite problem. I don't know all the details because they won't let me tell me. I don't have a high enough security clearance, and then I couldn't tell you anyway. This is a surveillance satellite, and it was surveilling something. And the problem was that it had to download the data down to the ground. And they got a red team of from the DoD who did their normal stuff, and they say, okay, we have to protect 3 servers. And so we have to do everything we can to keep everybody out of these 3 servers. And then we gave another red team, we said, okay, we want you to try our way of doing it. We're going to walk you through it and try this new thing. And they came up with a different problem. They said, no, we don't have to protect the 3 servers. All we have to do is protect 1 file, and only protect that file 1.5 hours a day when it's being downloaded. A much simpler problem. I mean, you could put an air gap, just disconnect it from the internet during that. I mean, there's lots of different, much better solutions for that. To protect those 3 servers and keep everyone out all the time, no way, never going to happen.
So last question. Well, we have 2 people that really, if they're quick, we'll have 2. Who you start, and then
my question is, like, when we're using a controller to ensure the safety and the security property of the system, who going to ensure the safety of the controller itself?
What was
who
the
will
one?
ensure the safety of the controller itself when you use a controller to ensure the safety of the system? So I think he assumes that in your methodology you introduce a controller at runtime to ensure safety. But
Yeah, there's always a controller in most of these systems. I mean, you look at an airplane or a car or anything, there are controllers.
And I think he wonders
I
what
think
happens
so.
when it has a safety problem. The
Oh,
controller
You're
has
adding
a
the
safety
controller,
problem.
I mean, you're adding something new into a system, and this
yeah, but the controller isn't unsafe. Software is not unsafe. It doesn't explode. It doesn't catch on fire. The worst it can do is give you an ulcer. It's not unsafe. This is a system property, and it's only the whole system that includes the controller, but it includes the other unsafe parts of the system that we worry about. It's only when that controller is controlling something unsafe.
You know, I think we should take this one offline because I want to have the one very last question, but then you're welcome to come up and talk with Nancy as long as she's willing to stay. So
Yeah, I'll
go
be
ahead.
around for a while.
Okay, so given that much of this model is based around the idea of the interactions of different systems and being able to preempt the possible problems that can arise, wouldn't being able to preempt these sort of problems require knowledge of different systems? And so whoever is involved in either just simply looking over this or whoever is designing the original system who wants to be able to preempt these problems, wouldn't this mean that everyone involved would suddenly have to have a lot more knowledge of not just their own areas, but whatever areas they could possibly come into contact with?
Well, I don't know what you mean by everyone has to have a lot more knowledge. If I have somebody designing a nuclear power plant and they're not a nuclear engineer that knows how to design nuclear power plants, we're in trouble anyway. This is done by the engineers. It doesn't have to be done by someone else. That's the problem with the old techniques, is that fault trees are really hard to do, and all these other things, they have to be done by specialists who don't understand the system. This can be done by the engineer as they're building. It's to help them think through their design as they're designing. And if they're not if they don't understand it, the engineering of that problem, they shouldn't be doing this anyway.
Okay, so then it's like a purely on a technical basis, and so they should only have to work with the logistics of it as opposed to the more mechanical issues, which would hopefully arise later in testing. And
well, I don't know, but testing, I'm not sure what testing has to do with it. Look, this starts at the system level, at a very high level. Did you notice that missile defense system? There are probably thousands of people working on that around the world. But we can abstract to the highest point, which is, again, what we're doing, system engineering. It's a top-down technique. And because it's top-down, it's much more efficient. Because when you're bottom-up, you have to go through everything. This says, understand the problem at the highest level. If we can solve it here, if we have a design solution, stop. If we can't, I'm going to have to go down and deeper into that subsystem. And so, but hopefully you'll never have to get down to the bottom. And you'll be able to find a solution without having to get down to the lowest level. I mean, we rarely get down to the atomic level when we're designing a car. The problem is we have to look at the car as a whole. Right now, the problem that the car manufacturers have is in the past they have been able to componentize. And what that means is the powertrain engineers were here, and the steering system people were here, and the other people were here, and they designed them separately, stuck them together, and the interactions were very simple. Now we have computers that are coupling all this stuff in magic ways, and we can do wonderful things. But we couldn't do it with electromechanical systems, those functions. It's because the computer couples this. So as we're turning a corner, we can change the chassis tilt. We can actually even maybe change the pressure in the tires. I mean, we can do all kinds of things. But that makes it all coupled, all connected. And that's where our problems are coming. And the car companies are really running into this. And the other people are too.
Well, I think we need to conclude, but thank you for a really illuminating and thought-provoking seminar. I hope you had fun.
Oh, I do. I always have fun with this.